In chapter 9, we are going to talk about the nonlinear design models. Oh yeah, assignment 0 is an error on Canvas. I kind of made a, I actually, I should not have published it. It was assignment from the previous class. So don't worry about it. So that nothing, no submission required. I would delete or unpublish the assignment today. So it was from the last uh, uh, session. Anyway, so we are going to talk about nonlinear design models. In nonlinear design models, we are going to review some of the linear models and linear design models that we studied earlier. And then we are going to extend these models for the nonlinearity application. This is a little bit review of the previous chapter and also introducing some new concepts. But this chapter is very important because after understanding this chapter, you will understand the fundamental equations that you need to implement in the autopilot to make autonomous navigation and guidance possible. So again, we are going to talk about what equations actually are programmed or governed inside the autopilot that makes this UAV fly autonomously. So this is the path that we have been taking. We looked at the unmanned vehicle. Clearly, the sensors on the unmanned vehicle are noisy. So we need some type of a state estimator. Then we have an autopilot that is used for stabilization, roll, pitch, and then we have some type of heading control. Then we supply some commands from the path following algorithm. These commands are going to be airspeed, altitude, heading, etc. And these commands basically come from a higher level controller, which talks about what type of path to take. And at the very basic, if you think about path manager and path planning, if you think about it, it's something similar to the waypoints navigation. So for an example, you have to go from point A to point B, and the path following and path planning algorithm is going to come up with the intermediate waypoints to make sure the UAV goes from intermediate points so that it can follow the speed, heading, and other requirements that are needed to satisfy the mission. So it is exactly same as the trajectory planning problem that we studied in articulated robots. So when we are trying to talk about the kinematic and dynamic models, kinematic models do not include any type of mass or inertia effects. Dynamic models include the forces, moments, and masses and inertia effects that make that whole system work. So when we are trying to design an autopilot, clearly we can't use the 12 state equations that we studied earlier, because it may be easier to solve those 12 sets of nonlinear differential equations inside the MATLAB or in Python on a computer, but certainly it's not possible to solve these equations or use those equations on an embedded processor like Arduino. One may say, hey, why not to use Raspberry Pi or BeagleBone or something else, which is computationally more powerful. But the unfortunate part there is these devices are power hungry. So they consume the lot of power, and with power, basically you need to supply with batteries, and that affects the endurance of the UAV. Also, many a times you have to perform quite a lot floating point calculations, which involves matrix inversion, approximation of sine, cosine, etc. And so in some instances, these calculations give rise to floating point errors and accumulation of residual error. Sometimes you can get 1/0 type of computation, and that actually causes that microcontroller to reboot. And worst thing that can happen to a flight control system is rebooting in flight. We don't want that to happen in flight. We don't want that to happen without uh, actually someone initializing it. We want the algorithm to be robust. We don't want processors to have silicon faults, because even though your algorithm is robust, even though everything is working fine, sometimes certain instructions get written at certain memory location that could have a silicon fault, which means something is not mapped correctly, something doesn't get written correctly, something doesn't get retrieved correctly. And that causes the cascade of bad events that can lead to a complete aircraft failure. There are mechanisms to prevent that, but at the end, again, it is recommended that if you are looking for aerospace and defense application, you work with the hardware that is certified for aerospace and defense, which actually ensures that there are internal hardware and software checks at the silicon level, at the processor level, to minimize processor faults. And that is very important. So it's not a good idea to save pennies by using the hobby grade processors or hobby grade microcontrollers or hobby grade electronics when you are actually developing that for uh, the real aircraft application. And there is a whole industry, and there is our hardware design rules. The other thing is, you would also notice, and this is just a general information, that aircraft industry is still not migrated on 3 nanometer, 5 nanometer, 7 nanometer chipsets. And the reason for that is they still are on 40 nanometers and 30 nanometers processors, because they are proven, they have been tested, that they have been vetted for thousands and thousands of miles to make sure that the system works. Even though this new technology is good, unless it's completely tested, vetted, and approved by FAA, it won't be part of the mainstream aircraft industry. So that's why it takes a little bit of time. So we have kinematic models, we have dynamic models. Idea is we try to come up with some reduced order models, the models which are smaller in size, less complex, that can give us fairly decent and accurate results. So if you remember this, and believe it or not, this summarizes our entire chapter that we studied for, I think, for 2 weeks, 4 to 5 lessons. Believe it or not, this is all the control loops that are implemented in Autopilot. So you have these equations. So first equation that you see is for airspeed hold. Second equation that you see for the roll hold. Third equation you see for the altitude or the height hold. Then the fourth equation that you see, so the first equation you see here is to maintain constant airspeed. Second equation that you see, that is implemented in the autopilot, that is for the roll hold. Third equation that is implemented in autopilot is for the altitude or the height or elevation hold. Fourth equation that you see is the course hold, which is chi, which is heading plus side slip or wind gust effect causes chi, which is the course angle. And then alternate way of, if you ignore the disturbances because of the wind, then you have alternate formulation. I'm going to call this 4A and 4B. 4B gives you the heading loop hold. which is nothing but when you have no wind disturbances, your course and heading becomes the same. And then you have the fifth equation, which is on the flight path. And then the sixth equation is on the load factor. This load factor is nothing but the thrust equation that basically actually gives you some equations that to be implemented in the autopilot. Now, some of you may say, is there any other way to implement the autopilot? Now, again, if you look at what we have here, is they are the simple PD type of controls, PD controls, which is proportional and derivative controls on airspeed, roll loop, altitude, the chi for A, for B, 5, and 6. So if you somehow, and I can relate to this because the very first autopilot that I wrote, which was on Arduino, actually implemented these loops. The problem there is you will have to use lots and lots of interrupts to make sure that these loops executed they get executed in proper sequence, because you cannot have a 10 or 20 or 30 seconds gap between updating one of these control variables. So nowadays what happens is typically you have something called as the real-time operating system. So RTOS. So you have something called as real-time operating system. Think about it like a Windows or Linux. Windows or Linux on a microcontroller or microprocessor. And what you have is you have this microprocessor. This is actually dealing with thousands of processes at the same time. Now, this is exactly what happens in our computer. So when we move the mouse from point A to point B, or when we type something on the keyboard, when we open up a program, operating system is sequentially executing these commands in the background. But this execution is so fast that user does not understand it. We don't see the difference because the processor is working at gigahertz. These instructions are executed very fast. And what operating system does is operating system is actually the layer that will coordinate the function calls, and these 10, 15, 16, 17, 100 processes happening in sec per second, and making sure these processes get executed. For an example, there is data retrieval from the hard drive. Data gets written to the hard drive. Internet, you get a data packet from internet. The data packet needs to get loaded. All those stuff like low-level hardware, device drivers, interaction with the external programming, and interaction with user, and getting some data or connecting with the Bluetooth headphone, mic, mouse, all that wireless interaction, that all processing, sequencing, assigning, prioritizing, terminating is done by the operating system. Typically, if you use an Arduino and then just write a simple sketch and try to execute that sketch, you can do this sequencing and prioritizing and conditional execution using something called as interrupts. So you can generate a interrupt in the process. The processor stops everything, executes that, and then goes to the next step. But imagine if you have maybe hundreds of processes. You can't just create interrupt for those hundreds of processes. The processor will break down. It cannot handle. So for that, what you need is you need an operating system. Now, in case if you are wondering, Parrot Mambo actually has a microprocessor inside. It's an ARM Cortex A9 microprocessor that actually runs embedded Linux. And that allows that Parrot Mambo drone to function the way we want. So believe it or not, inside the Parrot Mambo, there's an ARM A9 processor, and that ARM A9 processor is executing embedded Linux so that your MATLAB clone can run on that embedded Linux, and then basically you can actually interact with MATLAB or interact with Parrot Mambo using MATLAB. So all that stuff goes behind the scene, but as a user, as a programmer, once you have RTOS handled, or if you have embedded Linux, or if you have some other embedded programming operating system, you would be implementing these 6 equations and few variations of their variations that will get you a very simple flight control system. Clearly, these are the autopilot models. So you are going to have some stabilization, low level control, and then this autopilot control would work on top of that low level control. But this is the bare minimum, bare bone autopilot is these equations. Now, the next thing that comes in the picture is kinematic model of controlled flight. And believe it or not, this is exactly what we studied in the previous chapter. So we have the ground speed in the inertial coordinate frame, which is nothing but Vg. And then what we have the course angle, and then we have the gamma. So which is we have chi and we have gamma, flight angle and course angle that allow us to map the speed of the aircraft as on ground, as if aircraft is traveling on ground. If you were to find out the Pn dot, Pe dot, and H dot, which is the velocity in inertial velocity in north direction, inertial velocity in east direction, and inertial velocity in down direction, the Vg can be mapped with Pn dot, Pe dot, and H dot. If you were to add the wind triangle, the wind in the north direction, east direction, and down direction, equations for Pn dot, Pe dot, and H dot. Again, please understand, all these equations are these values are in inertial frame or fixed frame. So these values are in fixed frame. So you have this frame that is fixed. And what we have is we have the velocities in north, east, and down direction. So how can we proceed? And again, this is just a quick review of what we studied earlier. So if you make a first level assumption that you are in the level flight, which means the aircraft is not climbing, your gamma is equal to 0, and you do not have the wind in the vertical direction, which is no downward down component of wind, your equations get simplified, and you have just the equation for Pn dot, which is the north velocity, and Pd dot, which is nothing but purely dependent on the heading angle. So please understand, when flight angle is equal to 0, cosine of flight angle becomes 1, and all your relationship, basically you get a component of VA, which is the airspeed, and that allows you to find out Pn dot, Pe dot, and H dot. We also talked about something that is coordinated turn, which means if you have an aircraft that is turning, please understand, aircraft don't turn, which means aircraft don't turn like cars. If an aircraft has to turn, it has to roll, and that is called as banking. Banking is simultaneous turning and rolling. Cars don't bank. Basically, boats bank, and aircrafts bank. Bank means basically you get actually turn and actually roll at the same time. And probably if you were to see any aircraft turning, you would notice one side wing going up, other side wing going down. That is called as sort of the coordinated turn maneuver. And then the equation for that is starts with chi dot is equal to G over VG, the equation that is shown here, first equation. Then if you neglect the down component of wind, you get equation number 2. This also we studied, and that equation basically leads to the equation in heading rate, which is yaw rate. And then if your airspeed is constant, you get the condition for the coordinated turn that actually relates a constant heading rate. So please understand, if you are going to turn, this indicates turning. So you have the heading velocity, which means the aircraft is turning. That gives you, for left hand side to be equal to right hand side, to achieve equilibrium, you will get some non-zero value of roll. That's what it means. Next part is, this is also we looked at, which is the accelerated climb. If we were to look at the forces that actually are acting on the aircraft, they are lift and drag. You will realize that you can actually come up with an equilibrium equation, F lift cosine phi is equal to the gravitational component and mass of the aircraft and the ground speed and gamma dot. So if you look at the gamma dot, if you take on one side, you get this equation, and that gives you something called as the load factor. Load factor equation is nothing but lift, the force of lift divided by the weight of the aircraft. So for the level flight, the load factor is 1, which means the weight of the aircraft is equal to the lift. So the aircraft is not climbing, aircraft is flying straight. And this equation, basically, when the load factor is equal to 1, that you can substitute, and then you have this equation for the load factor when the climb rate is 0, when the aircraft is in constant climb. So these equations are pertaining to certain aircraft maneuvers. Now let's quickly look at the kinematic guidance models. And please understand that the models that we are going to discuss here are full nonlinear models, unlike the previous case where we looked at the linear models. So again, you have the choice, and depending upon the aircraft that you are designing, you have certain guidance models. If you have some experience in working with paparazzi or Autopilot or Pickhawk, any type of autopilot, one thing you have to see is you can use the same hardware to design or to implement an autopilot for fixed wing aircraft, different types of fixed wing. So flying wing aircraft, you could have the conventional aircraft, you can have the aircraft with a combination of elevons or some other control surfaces. We modified that software to fly parasail. Based on parasail, our student in our car, Lucas, is going to present his Barrett thesis. And I would encourage you, I don't know if Lucas is attending in today's class, but Lucas, if you are attending, then you are welcome to let everyone know about your Barrett's thesis defense. That is tomorrow. So he actually implemented autopilot for his parasail UAV. So I would encourage you to attend his Barrett thesis tomorrow. Next thing is kinematic guidance model. And this is the very simple model. This is exactly what I implemented. You can implement a simple kinematics guidance model, which is giving you the relationship between various velocities, north velocity, east velocity, the differential loop on chi, differential loop on height, and then airspeed. And then you get the equation for the heading that is shown over here. And this is the simplest model. And understand that when we are going to look at the path planning and when we are going to implement the path planning for simple uh, tracking or simple paths, we are going to use this model because this is the simplest model, easier to implement, can run on a low power, low cost microcontroller. So this is the kinematic guidance model. We can actually make this model slightly different if we are going to use the heading as a command. Then if you, so what it means by that is if you use psi as the command signal, then you can, the kinematic guidance model gets slightly changed. But these kinematics guidance models are actually for simple aircrafts. If you are designing for F-16 or some other fighter planes, then these models won't work. But for simple UAVs, these kinematic guidance model, they work very well. And at least in my experience, they are easier to implement. Then if you want to make it a little bit more accurate, and actually you want to implement a low level control on the roll angle, and if your aircraft is actually performing a coordinated turn, for an example, you want that aircraft to loiter, or if you want that aircraft to perform certain maneuvers, or if your path is a straight line, curves, turns, that type of stuff. So you would use combination of straight line guidance and turn models. So you have this roll angle and coordinated turn model that can be used as a guidance model. And again, what we are doing is we are sort of aggregating the equations that we saw earlier in this lesson, earlier in this class, and we are aggregating them together just to come up with a better approximation of the trajectory or maneuver. So this is the kinematics equation that they get implemented on the autopilot. And what I'm going to do is I'm going to spend some time and I will show you how these autopilot equations are written for our MAV simulation. That will give you better understanding of how these equations are implemented. Now, you can actually rewrite these equations. So you have the slight variation wherein you get the wind north, wind east from the wind triangle, and then you compute chi and the ground speed. And again, these computations are performed by the autopilot. And depending upon whether you have a pitot static tube or whether you have some type of aiding, or sometimes if you have the local wind data, depending upon what navigation and aircraft information or weather information that is available to you, you can use the appropriate model. Many a times you have something called a state machine, wherein depending upon the type of data that is available at certain instance, and depending upon the flight regime that you are in, you use appropriate models. Then again, variation is if you want to perform the flight path control. So you have this flight path angle, which is gamma, that you can actually implement. And then that actually gives you a little bit more accurate model. And which model you choose, it's up to you. My recommendation to you is start with the very first one because it's easier, it works, and it can be implemented for a large class of aircrafts. So you have PN dot, PE dot, H dot, psi dot, gamma dot, VA dot, and phi dot. So these are the different equations that need to be implemented subsequently, sequentially inside the autopilot. And then what you can do is, if you want to make it even further, you can add the load factor to it and then supplement this equation for the load factor, which is given over here. And that gives you even a more accurate model. So if you want to add the dynamic model, then you need to take into account the external forces, which are nothing but the drag force and the thrust force. So thrust force is basically the force given by the prop. It could be a puller prop, pusher prop, side prop, which are the props on the wings. So you can have, or you can have prop on front, you can have a prop in the back. So you have different prop configurations. And again, you can actually incorporate the effect of forces, the thrust force, the drag force, and actually modify these models that we talked about. And finally, what you have is you get an equation for VG dot, that is the acceleration, which is you have the ground speed, the rate of change of ground speed. And believe it or not, the first equation that I have shown here is a form of force is equal to mass times acceleration. And then finally, we make some changes. We actually get the equation for chi dot. And then at the end, if you want to look at the dynamic guidance model, we are looking at the same equations that we saw earlier, but now we are incorporating these terms which are shown in blue and red. So these are the terms that pop up if we include the lift force, drag force, and the thrust force. And you can actually use this to find the airspeed VA, and then you can use this to find out. So this you can use to find airspeed, and you can use to find heading. And all these equations together provide you a comprehensive designs equation set that can be used for your autopilot design. Now, a word of caution that unless we implement these equations inside the MATLAB, or unless we implement these equations on an embedded system or on a processor, it's very difficult to appreciate the power, or it's difficult to appreciate what these equations imply physically. So when we are actually going to do the MATLAB exercises where we are going to design the autopilot from scratch and use that autopilot to fly our MAV from prescribed path, everything will make sense. But right now, what I want you to understand is these are the equations, and these equations are shown in continuous domain. But what we do is we actually use the discrete or digital versions of these equations and program those on autopilot, and then use that autopilot to control the control surfaces and the information that we need as we integrate or execute these differential equations step by step in a discrete form. We are going to use the sensor data that is coming from the aircraft sensor, like accelerometers, gyroscope. And in between, sensor data is noisy, so you would have some type of estimation scheme that will take this noisy sensor data and actually feed that data to these equations so that these equations can propagate. Now, please understand, these equations are dependent on time, which means what needs to happen is as time advances, we need to find out the next value of the certain variable. But the next value of that variable is dependent on the measurement that is coming from sensor, and it is also coming from the previous state that we calculated. And again, so you get a very nicely written code or architecture that includes Kalman filter, discrete time integration, and some type of error checks to make sure that the faults don't occur. Now, at the end, if you don't assume any wind, if the aircraft is flying in a very low wind condition, Wn, We, and Wd, the component of wind, can be ignored, and these equations assume a very simple form that can be used over here. For example, if you are trying to implement the equations for parasail or a small aircraft, clearly the small aircraft, the airframe itself is so small that it cannot withstand wind. Paracel UAV, the airframe cannot withstand wind. So you can actually start with a very simple dynamic guidance model, which is presented on this slide, and develop an autopilot rather than going to the complex wind models that actually are used inside the autopilot loop. So at bare minimum, these are the equations that we need to implement inside the autopilot. And this is the crux of the last few chapters, last 3 chapters that we talked about, that is summarized in this chapter. So our next natural extension is to take all these equations and develop the autopilot code and the state transition machine, finite state machine, and then implement that in our MATLAB code so that our aircraft can fly autonomously. So this is a small chapter, but with that we have finished about more than about 75% of the textbook. Last few chapters are sort of common between all the different types of robots. So what I would do is I would use combination of in-class instruction, webinars, and MATLAB virtual labs to convey or to discuss the material. But with this, I will stop here. If you have any questions, I would be happy to answer. I would fix the assignment on Canvas. That way you can upload your answers. And I wish you all a good weekend. I would be happy to answer any questions you may have. Or I will see you on in next class on Tuesday.